Thanks, Lex, for an introduction, and I'd like to start by thanking the organizers for inviting me and organizing this nice conference in this nice place. So I'll be talking about certain norms which are defined according to some graph structures, and then among applications I'll mention this one to this nice conjecture of Erdos-Simonovits and Sidorenko. Okay, so let me just introduce the notations that we have seen several times in this conference so far. So I'll use a slightly different notation that for a fixed graph H, I'll denote by T sub H of G this usual homomorphism density. So we look at the random maps from the graph vertices of the small graph H to the big graph G, and we are interested in the probability that this preserves adjacencies. So it's a graph homomorphism. Now, we can express this, as we've seen before, as a formula in terms of the adjacency matrix of the big graph G. So we go over all the edges of the graph, small graph H, and we look at this product. Now, we have these random variables x sub u, where u are the vertices of the small graph H, which tells us basically where this vertex u is going. Or which vertex it's being mapped to. So these are IID uniform random variables taking values in the vertices of the big graph G. They kind of define our random map. And this product is 1 if and only if the map is a homomorphism. So the expected value just gives us the probability. Now that we have this nice formula, we just look at the adjacency matrices. We can look at any matrix, or in fact, any symmetric, let's say, measurable function on this fairly general setting, let's say, from 0, 1 square to R. And we define this TH of F as the similar expected value. Now, so an important example is the C4 one. So I just wrote the formula. So if you look at the indices, they form the C4 cycle. So we are interested in these kind of products. So there's an underlying graph structure here. Now, the C4 has some interesting properties. So first of all, it's always non-negative. It's not so hard to see. You can write it as expected value of the square of another expected value. So it can never be negative. And another interesting property is that actually it's 0. The only function that makes it 0 is the 0 function. Now that we know it's non-negative, we can define this function, take its fourth root. It's going to give us a non-negative number. I'll denote it by this C4 norm of F. Now, so there's a reason that I'm using this notation. So it has some properties. One is that it's homogeneous with respect to scaling. So if I multiply F to this any scalar lambda, I can just take it out and it will be absolute value. So it's homogeneous with respect to scaling. And another important property it has is that it's subadditive. So it satisfies the triangle inequality. So it's not trivial. So you need to prove it, but it's not also a difficult proof. It's just a bunch of Cauchy-Schwarz inequalities. So we have this property, this and that, which basically tells us that this is a norm. So it satisfies the 3 axioms of a norm. And the natural question that arises, and it's been asked by Latzi, is that for which graphs H we get a norm if we look at a similar formula. So I'm looking at this thing, and I take the absolute value to give it to make it more likely to be a norm, and then take the proper root. And we're interested in the question that for which graphs H we get a norm if we look at this formula. So one example that we know here is the C4, but there might be other examples. So the question is a bit robust, so we can also look at this other version where we are only interested in positive functions. So basically what I'm going to do is I first take the absolute value of F to make it a positive function or non-negative function, and then apply the formula. So I'll denote this with this absolute value here. So there are 2 variations which I'll be interested in. And M is the number of edges in H. And let's go over the axioms of norm. So let me start by homogeneity. So the formula is defined in a way that the function is this norm function that I define is always homogeneous. So this is always satisfied. It's trivial for every graph H because of just the way that I define this formula. The second axiom that I want to look at is non-degeneracy, that the only vector that has norm 0 is a 0 vector. And this turns out to be not so difficult, so we can understand that in which cases we get this, assuming that this function is a norm. So the whole difficulty is in the triangle inequality. That's the heart of the difficulty of the question. So basically, we want to understand for which graphs H we have this function that we defined here satisfies the triangle inequality. And I'm using this notation, by the way, regardless whether this is a norm or not. So it's a bit of abuse of notation, but I think it's OK, hopefully. So let's go back and look at the formula of this. So first of all, note that if I suppose that H is not a bipartite graph. Then if I take F to be the adjacency matrix of a bipartite graph, I'm going to get 0 here. So non-bipartite graphs cannot lead to a norm, but they might still satisfy the triangle inequality. But actually, that's not also true. So it's a very easy, you can just cook up some easy example which shows that H has to be a bipartite if we want to get a norm. So we can restrict just to bipartite graphs. And in this case, now that we know that H is bipartite, we can look at this more general case where F is not necessarily symmetric. So now F is an arbitrary function over a product space, X and Y. So these are both, let's say, measure spaces or probability spaces to R. And I'm looking at this product, the same thing, but now I have two sets of random variables. Y's take their values according to the space capital Y, and X's, they take values according to the space capital X. And because I have this bipartite structure, some vertices correspond to these X variables, the other vertices in the other part correspond to the Y variables. So this, although might seem a stronger condition, it actually turns out to be equivalent. So this symmetry thing here is kind of misleading, and it's redundant. We can get rid of it, and we are not losing anything, and we are not gaining anything. So I'm going to focus on this more general setting. F is just an arbitrary function on a product space, and because H is bipartite, I can look at these formulas. Bipartite homomorphisms, kind of. And also another thing which comes out of the proof is that the question is equivalent for finite and this, let's say, 0, 1 square setting. So it's always a norm if and only if it's always a norm for the case where X and Y are finite sets. So they are, say, uniform probability measures over finite set, which basically means that F is a matrix. X corresponds to the rows and Y corresponds to the columns. So there are no real measurability difficulties in this question. It's a very combinatorial question. So let's start to prove things. So let me start by just reminding you of the definition of tensor. Suppose I have two functions, f and g. They are from the product space to R. Now, their tensor is defined as just the usual tensor of matrices. So this is a function from x squared times y squared to R. And now, how is it defined? So for a pair xx prime in x square and yy prime in y square, the value on this is just the value of f on xy times the value of g on x prime y prime. It's just the usual tensor of matrices. So you get this independence kind of thing. F acts on the first coordinates and g acts on the second coordinates. Now, it has some nice property for us, because if you look at this formula, if I write this thing here, I'm going to get independence. So I can write this expected value as the product of two expected values. So basically, these densities, homomorphism densities, they are multiplicative with respect to this tensoring property. So I have this identity, simple identity. And it turns out to be really useful. So let me introduce another notation. So we are working with this bipartite graph H. Let me put an order on the edges. So let me give them names. I have m edges. Let me call them E1 to EM. Now, suppose instead of one function, I have about m functions, actually. So for every edge, I have a particular functions fi. Now, I define this product over h of these functions as the same expected value as I had for a single function. But now, for every edge, I just put the corresponding function here. So instead of f, I have fi when I'm looking at the ith edge. So it's the same product, but with several functions. So it's a nice notation. I can express now my norm formula in this notation as just the product of f by itself, taking the mth root. And it's kind of parallel to the usual Euclidean norm in terms of notation, that the Euclidean norm of a vector is just that product and take the square root. So let's make some observations before proving something. So one is that this product notation, this product function that I defined is linear in every fi. It's just because of the formula. If I have fi plus fi prime, I can expand it and I get linearity. The other is that, similar to what we saw in the 2 slides ago, is that we have multiplicativity with respect to tensoring. So if I have 2 sequences of functions and look at their tensors, I can just write as this product. And the other thing that you can observe is that also our norm, or whether it's a norm or not, this function is multiplicative with respect to tensor. So we have these 3 simple observations. Yes? Because it's not f times g, it's tensor g. So it's kind of, you'll get different, so it's kind of like looking at f of x times g of x prime. There will be independence, complete independence. So the first thing I want to show you is this theorem, which says that this function that I defined is a semi-norm, meaning that it might not satisfy the first axiom, in the non-degeneracy axiom, but it satisfies the triangle inequality, if and only if a Cauchy-Schwarz type inequality holds. So I don't care for this about this condition for now. I'll come back to it. So I'll just care about triangle inequality. And it says that it's equivalent to this seemingly much stronger condition, that if I have any set of functions f1 to fm, their product is bounded by the product of the norms. It looks like the usual Cauchy-Schwarz inequality, that the dot product of 2 vectors is bounded above by their norms, product of the norms. So one direction is easy. I mean, this is a very strong condition, so there is no surprise that we can get triangle inequality from it. So let me show you the proof of that. So suppose this holds for any set of functions. I want to get triangle inequality. So what is the h norm of f plus g? It's this mth root of this product, and let me raise both sides to power m to get rid of this mth root. So I have this. Now, this is a linear function, the product. So I can expand it in the first coordinates, write it as the product of f and these f plus g's plus the product of g and f plus g's. Now I can apply my assumption that this Cauchy-Schwarz type inequality holds. So this one is bounded by the norm of f times the product of these things. So I'm going to get m minus 1 copies of this norm of h. And I get the same thing with g instead of f here. So if this holds, we show that the mth power of h norm of the sum is bounded above by this, which I can factor out this part. And that's just triangle inequality. So triangle inequality follows from this with the usual way of proving it for LP norms or anything. Now, the proof of the other direction, we're going to use this tensoring properties that we saw. So now we are assuming that the triangle inequality holds. We want to show that for any set of functions, we have this Cauchy-Schwarz type inequality. And how does the proof goes? It's by contradiction. So suppose I can find a bunch of functions such that their product is larger than the product of their norms. Now, for now, let's assume that none of these norms is 0. So we can normalize and assume that all of them are actually 1. Both sides are homogeneous with respect to scaling. So I can scale all these functions to make sure that they all have norm 1. Now, so let's look at this sum. I'm taking each one of these functions, raise it to 2k tensor power, where think of k as some large integer, positive integer. And let's look at the sum and take the norm. We are assuming that the triangle inequality holds, so I can bound this above by the sum of the norms. And I know that the norm is multiplicative, so this is just the h norm to the power 2k. And we assume that the h norm is 1. So we get this m uniform upper bound. It doesn't depend on k. So for any k, if I look at this sum, it's bounded above by m, just by tensor property and triangle inequality. Now, let's try to lower bound it using a different method. So by definition, if I raise this to power m, this is just the product of the sum by itself over h. Now, this product is linear in all coordinates. So I can expand all these sums. So what I'm going to get is the following. I'm going to get this huge sum over m to the m terms. And each term tells me which index I'm picking from the first sum, which index I'm picking from the second, and so on, and which index I'm picking from the last one. So the sum is over all possible I1 to Im. They are in the set 1 to m. And this product is just I expanded because of this linearity. Now, I know these products are multiplicative with respect to tensor, so this 2k comes out as a power. So all these numbers, now all these terms are positive numbers, non-negative numbers, because I'm working with reals for now. So I have this sum, and one particular term that appears here is the one where I1 is equal to 1, I2 is equal to 2, because this is over all possible indices. So this is in particular bounded below by this thing. But if this is larger than 1 because of our assumption, I can take k to be so large that this is a huge number, and even if I take its mth root, it's going to be larger than m, which I'm getting a contradiction. So I can make this large enough because there is one term which is larger than 1m, and I'm raising it to power k. So it's a simple proof, just using a simple trick with tensors. So we showed this. And it has some interesting corollaries. So one is that if you can answer the question for connected graphs, then we know the answer for non-connected, for every graph. Another consequence is that, so that's the non-degeneracy condition. So this doesn't talk about non-degeneracy, but it's possible to deduce from this that the only possible norms which are semi-norms but not norms are the ones defined by stars. So this non-degeneracy condition only, if you're talking about semi-norms, the only case where it's not satisfied are these stars. So it's not, we completely understand it now. These are not norms, but they are semi-norms. And if you look at any other graph which is a semi-norm, it's going to be automatically a norm. That follows. No, I think. Otherwise, it might be just the unions of just the same star, but no, not much. So also, we can use this strong inequality to get some other necessary conditions. So let me, before that, introduce some terms. So I'm going to call my graph norming if this function is a norm, and I'm going to call it weakly norming if the one with absolute value is a norm. And of course, the way that I define the terms, kind of implies that norming should imply weakly norming, and actually that's not so difficult to see. So this is a stronger condition to define a norm than to define it with absolute value. And so what classes are norming or weakly norming? Even cycles are norming. That's classical. They define just trace norms or shatter norms. You can express it in terms of eigenvalues. So that's been known for a long time. The other easy, not so difficult to show, are the complete bipartite graphs. So they're always weakly norming. Any complete bipartite graph is weakly norming. And in fact, if m and n are both even numbers, then they are norming. So they also satisfy they define a norm even without the absolute value. And another more interesting construction is maybe this recursive construction. If you take two graphs H and F, take their adjacency matrices, tensor them together, you're going to get a larger matrix, and that defines a graph. That graph also will be norming. So you can take any of these two graphs, let's say an even cycle and complete bipartite graph, tensor them, you're going to get a more complicated graph, which is going to be norming. So there is this way of constructing them using tensors. Another example which is norming are hypercubes. So they are weakly norming, actually. We don't know whether they are norming or not. So how do we prove that something like this is norming? So we want to show that this dot product, the Cauchy-Schwarz type inequality, this product that we define is bounded above by the product of the norms. So this is just the expected value. So what we're going to do is take this expected value and fix some variables, apply Cauchy-Schwarz, and fix some other values, apply the Cauchy-Schwarz, and we'll never actually get the right-hand side, but we will converge to the right-hand side. So this is different. Hypercubes, kind of, when we talk about it, kind of reminds people of the Garage norms or the octahedral norms, but this is different. It's the graph norm defined by a hypercube. So it's not the same proof. It's infinitely many Cauchy-Schwarzes in a sense, but it's combinatorial. It's just a bit involved to keep track of what's happening when you apply these Cauchy-Schwarzes and exploit all the symmetries of these hypercubes. Okay, so hypercubes are weakly norming, and a question that I don't know the answer is that whether even dimensional hypercubes are norming. So odd dimensionals, they cannot be norming because they can be zero, and I know when something is a semi-norm but a norm. But even ones, I don't know the answer. So n equals to 1 is the C4, it's a norm, but the next one is Q4, which is on 16 vertices, and it's too big for, I don't know, applying flag algebras or something to resolve it. So I don't know the answer to this. And also some necessary conditions that one can get from the Cauchy-Schwarz type inequality. So I also already mentioned that the graph should be bipartite, and a very strong condition that you can get is that the vertices in the same part have the same degrees. So it's kind of bipartite regular. So it's like K, M, M. The vertices in one part, they all have degree M. The ones in the other part have all degree M. So it's a very restrictive property, but still we cannot still characterize all the graphs. And another property is that subgraphs cannot be denser than the original graphs. So for any subgraph K, the density, there is this -1 technical thing, but the density is basically bounded above by the density of the graph. So let me also mention some generalization of this framework before going further to applications. So we look at these norms defined by graphs. So the first natural thing that comes up to mind, why just look at graphs? Let's look at hypergraphs. So instead of two variable functions, we can look at k variable functions, just look at the same formulas, same type of formulas. So that's a natural generalization. The other thing is, so let's also allow complex valued functions. Now we have to take conjugates and stuff, and also we can allow, why just allow power ones? Let's allow non-integer, non-integer or not like integer larger than 1 powers. So we can look at these kind of products. And the good thing about this more general framework is that it includes the LP spaces. So you can do LP spaces where alpha I is equal to beta I equals to p half. So it's a class of norms which contains all these octahedral norms and also LP norms, some classical norms, or shatter norms, so some nice classes of norms. And I'll denote this by this notation of h alpha beta corresponding to these powers, and h is the underlying hypergraph. So we might look at some formula like this and ask whether this is a norm or not. Now, so one obstacle is that the previous technique was too combinatorial to work here. Namely, we cannot just look at this f plus g and expand things. So we have to do more analytic things. But fortunately, the derivative will be enough to start with. So if this is a norm, then if I look at the derivative of f plus tg in terms of t, by triangle inequality, this is, of course, I can write in this, bounded above by this, so I get this upper bound of norm of g. So basically what I'm saying is that the derivative of f plus tg in terms of t is bounded above by the norm of g. Now you can write a formula for derivative, yes? So yes, one thing is that
what was the question?
how can we guarantee that the derivative exists? Yeah. So I said that it's enough to say these questions for finite, actually the sets on finite, measures on finite sets, so then everything is just polynomials. And for general case, you can approximate, and it's not such a, if you want to do it a different way. Now we can write the formula, then apply the tensor trick with some difficulties, but it's possible to do it. And we get Cauchy-Schwarz type inequalities. So the Cauchy-Schwarz type inequality that we had before was really neat, that for any set of functions we had this. But here we need to assume some extra conditions. So basically I have this hypergraph with these weights alpha and beta. I decompose it to different hypergraphs, so sum it as this sum of hypergraphs with weights. And the analog would be to have this for any set of functions f1 to fn. So if I look at the product defined by the first one times the product defined by the second one, and so on. But here we need to require that, well, either all the functions are positive, or we are in this nice combinatorial setting where alpha I and beta I are actually integer, so we can expand things. But, okay, so we have this Cauchy-Schwarz type inequality. And we can use it, and actually it turns out this more general setting is not much harder than the previous setting. So it turns out that if you have a norm, either it's very similar to what we had before, all the powers are 1. So I have these two products, both on m edges, and these m edges are disjoint, so no edge appears in both products. So for some of them, for these ones I have the f, for the other ones I have the conjugate of f. So this is really like graph norms, but the only thing is the complex conjugation. The other type of norms that I might get is with absolute value. So I take the absolute value, raise it to power alpha, and this alpha is uniform. So this allowing different powers is not really going to give me any new norms. And this is basically a norm if and only if it's a norm for alpha equals to 1. So the question didn't become much harder, although we consider this more general setting. But it's a nice thing. I mean, you can say, look at this formula, which is just C4 norm of f squared. I took the square root. And it's not a norm because the powers are not 1, and they are not all absolute values. So you can overrule these kind of cases. And the proof is not really so trivial, so it had several steps. So another thing I want to mention is this. So this is a more recent work. There are analogs of this norm. So the norms that we looked at, they came from this sampling from graphs. But there is a parallel research going on groups, say abelian groups. We can look at the samplings there. So, and in particular, the analogs of these norms are they're important Gauss norms there. So now my function, instead of being a function product space, is just a function from my group from some finite abelian group to R. And I look at these kind of averages. So the expected value is now over f of these linear forms. So I have these random variables. These are my samplings. I pick one x, and I pick directions y1 to yk. And now I look at I move on different combinations in these directions and look at the value of f on them. So it's a hypercube, subcube basically. And look at the product and take the expected value. And that will define a norm for me. So these are called Gauss norms, Gauss uniformity norms. And they can be defined for complex valued functions. So some of these terms will be conjugated. So examples is U2 norm is defined this way. So there are 4 terms when you sample. These 2 are conjugated, and U3 is defined with 8 terms, and these 4 are conjugated. So it's really analog of what we have been doing with graphs and hypergraphs in abelian case. And they're defined in Gauss's Fourier analytic proof of Erdos-Simonovits-Sidorenko theorem, and they really appear in all the subsequent works, like the Green-Tao theorem and Balaj's work and many other related works. Now, let's try to be general in this setting too. So instead of just Gauss norms, let me just sample similar things. So I pick these uniform random elements in the group, and I look at these various linear combinations. They can be defined using a matrix. So it's really analog of what we are doing. So T sub L of F, where L is this matrix with positive integer entries. Now, when is this thing a norm? So Puya and Shachar extended the previous results to this setting. So these are norms if and only if this Cauchy-Schwarz type inequalities holds, and the similar things. And actually, in this algebraic setting, you can ask some very interesting questions which you couldn't ask in the graph case, or they're trivial in the graph case. So let me mention this question. So suppose that you have a graph norm. So suppose this is a norm, and it's actually a graph norm defined by a graph. Now, if I have a sequence of functions, bounded functions, it's really easy to see that they converge in the C4 norm if and only if they converge in the H norm. So, I mean, convergence is just, there is one convergence in graphs when you talk about bounded functions, and that's what's defined by C4 norm. So you don't get different notions of convergence. But, and similar statement holds for hypergraphs. But in this algebraic setting, this is not true. So, and examples are just Gauss norms. If you took two different Gauss norms, you can construct different sequence of functions such that the limit of the norm of the first one is 0, but the limit of the, say, UR norm of the sequence converges to 0, but UT norm doesn't converge to 0. So this equivalence doesn't hold. And actually, that's why you work with different Gauss norms. They kind of capture stronger and stronger notions of convergence when you increase T. So the natural question is that, so let's define two norms, say bounded equivalent, if they have this similar convergence when you talk about bounded functions. For non-bounded functions, yeah, all these norms will be different. But when we are interested in the bounded case. So we call them equivalent, and the question is that what are these equivalency classes of convergence that we get? And what Puya and Shachar showed is that so they looked at this group FP to N, one of the interesting cases in the abelian case where people look at, and they show that if P is large enough, it's larger than some constant depending on my system, then the norm is not something new. The convergence that you get is similar to what you get from one of the Gauss norms. So there is some K such that my norm is bounded equivalent to the UK norm. But this only works when P is sufficiently large. And there are two obstacles to generalize it to small values of P. One is that it uses higher order Fourier analysis. And not all tools from higher order Fourier analysis were available for the small values of P. So the inverse theorem is proved recently by Tao and Ziegler, but one needs more to actually be able to conveniently do higher order Fourier analysis. And the other obstacle actually comes from this thing about norms, so it's a more related to this topic of kind of obstacle. So we have been working on this with Shachar Puya, and now we can generalize the higher order Fourier analysis to lower small values of P, so that's not a problem now. But still we cannot solve the problem. So we can show that every such norm belongs to a certain class, but this class is a bit larger than all Gauss norms. So let me mention something explicit, that in particular, if you just look at an F2 to the n, and look at this norm, which is just maximum correlation of F with this -1 to a cubic polynomial. So P of x is something in n variables over F2. Write it as suppose it has a formula as a cubic polynomial. Take the maximum over all such functions, such polynomials, then this is a norm. And we cannot overrule the case that there is a norm defined by linear forms which is equivalent to this, bounded equivalent to this. And if that would be the case, it's different from all the Gauss norms. So there is no Gauss norms which captures this. So for Gauss norms, we need something which are called non-classical polynomials. And so this is a really difficulty which is not related to higher Fourier analysis, just about this norms. Yes?
But there is a Gauss norm, at least one direction, or if it converges in that, then it will converge.
Yes, yeah, if it converges in a large enough Gauss norm, or actually U4, it will converge. But yeah, but there might be, the opposite is not necessarily true. And another thing is one can look at other groups. So there has been works in generalizing this abelian case to other groups and ask similar questions about convergences. I think it would be really interesting if it turns out that there are other convergences which are not captured by these Gauss norms. But in abelian case, my feeling is that the answer is negative. So we cannot define such a norm. All right, so let me mention some the application to Erdos-Simonovits-Sidorenko conjecture. So the conjecture is, we can write it in the following way. Let H be any bipartite graph with m edges. Then it says that if you look at the edge density in F raised to power m, it's a lower bound for the edge density of it. So it's a formula comparing two averages. It's something really analytic, but it also has, of course, combinatorial flavor, extremal combinatorial flavor, because it's comparing edge density with density of the graph. And one interpretation that one can make is that among all random graphs, among the graphs which given edge density, random graphs contain the least number of copies of every bipartite graph. So if you want to minimize the number of copies of H, you just, one possible way would be to take just a random graph. And, but it might be other graphs too. But it's one interpretation at least, which has more extremal combinatorial flavor. Now, asymptotically, yes, everything is asymptotic. Thanks. It's for dense graphs, of course. And okay, so this is the conjecture as I wrote it before. Let me talk about the history. So the case where H is Pn, the path of length n is equivalent to some inequality about matrices from 65. So even that case is not so trivial. Then Erdos and Simonovits verified, they conjectured this here and verified it for trees and the three-dimensional cube. And the way that they formulated the conjecture is more combinatorial, so it doesn't talk about homomorphism densities. It actually talks about the edge actual densities. So there are error terms. But then this Sidorenko formulated in this nice analytic way and verified it for many other graphs, including the case where one part, your bipartite graph has one part which has at most 4 vertices, and some other classes of graphs. And there's been more work, I'll mention it in a minute after that. So, but let's see what does this conjecture means in our setting. So first of all, it's about non-negative functions. I can get rid of that by just putting absolute values. And also I can move this m to the other side, so I get this equivalent formulation for general functions. But then in my notation, this is just says that the K2 norm of f with this absolute value is bounded above by the H norm of f with the absolute value for symmetric f. And it turns out symmetric and non-symmetric is equivalent here. So that's not an issue. So in our notation now, this is the ESS conjecture. Now, what can we say about it? So let's look at this product that we had. And we know that there is this Cauchy-Schwarz type inequality. Now, suppose that my graph H defines a norm. Let's consider any subgraph of H. So K is a bunch of edges in H. I know that this Cauchy-Schwarz type inequality holds. Now let me set these functions to things that I want, that works for me. So I'm going to put f on edges where they belong to K. I'm going to put just constant function 1 on edges that don't belong to K. So now Cauchy-Schwarz type inequality is this. I have this product. I have a bunch of f's on the edges in K, and I have a bunch of 1s on the other edges. And what I have on the right side is the number of f's I get as a power here, and the number of 1s I get as a power here. And this is actually 1, so I can just remove it. So what I got is this. The product over, and this is product over K. The 1s, again, disappear from this product. So the product over K is bounded above by the product over H to this power. And I take the Kth root, so I get this inequality. So what we showed is that if this is a norm, then for any subgraph, we have this inequality. The norm defined by subgraph is dominated by the norm defined by H. And you can repeat the same proof with this absolute value 1, and you get the same thing, but with absolute values. And let's just compare it to the ESS conjecture, which just asks about K2 and H. So in cases where we know when this is a norm, we get something much, much stronger. Not only this dominates the edge dense norm defined by edge, also dominates any norm defined by the norm defined by any subgraph. Right? So this verifies the conjecture for all weakly norming graphs, in particular hypercubes. And actually, after this, there has been more recent work, and they're really nice. So one is due to Conlon, Fox, and Sudoku, which verifies for a very general set of graphs, which is the set of all, which is the case where H contains a vertex of full bipartite degree. So if you have even single vertex which is connected to all vertices in the other part, the conjecture is true. And Xiang Li and Balazs, they had this entropy-based or convexity-based method which verifies it for, I think, as Balazs tells me, it includes all the previous cases and it proves it for more graphs. And so, of course, this studying norm graphs is not the right way to try to prove the ESS conjecture, because as we already know, there are many graphs for which the conjecture holds and they are not norming. But it might be a good way to study the following case, which is for which graphs H, this density dominates all the subgraph densities of all subgraphs of it, K. So for which graphs H, for any subgraph K of H, we have this inequality. So this might turn out to be a class the same class as weakly norming graphs, but I also don't know the equivalent. So this much stronger result that I got might be actually equivalent to the weakly norming. So let me also, in the time to the left, talk a bit about geometric properties of this norm. So this is a bit, so not combinatorial, but I think it's interesting, and some combinatorial applications might come out of this someday. I don't know. So these are norm spaces, so we can look at them from, say, Banach space theoretic point of view. So in the Banach space theory, so one way of studying norm is to study their finite dimensional subspaces. And one of the things people do is try to understand how similar they are to LP spaces, and so which properties they share with LP spaces. There are various notions which capture this, like uniform convexity, uniform smoothness, type, cotype. So you show that the Banach space has type, say, cotype Q for Q larger than 2, then you know that in certain ways it behaves similar to LQ space, and so on. Now, so consider a graph H with M edges, and suppose that it defines a norm. So we know that the function defined by H is a norm. Now, let me just restrict myself to diagonal matrices. So these functions are applied to all general matrices, right? But if I just look at TH of a diagonal matrix, what I'm going to get is nothing more than just the mth norm of the diagonal, normalized in a certain way. Because everything is 0 except on diagonal. So when you look at these densities, you just have to go inside diagonals and take the mth power. So this space defined, I denoted by L sub H. The space defined by these H norms contain the finite dimensional subspaces of Lm as inside it, as a subspace. Right, so I can embed any finite dimensional subspace of Lm isometrically inside the space defined by this new norm, just looking at diagonal matrices. So this tells me that my space cannot behave much better than any better than Lm space. In other words, if you look at the unit ball of this space, it has sections which correspond to unit balls of these Lm spaces. So its smoothness, convexity, all these things are not going to be better than Lm spaces. Okay, but does it behave worse, or can we show that it has the same convexity, say, as the Lm space? And the strongest way to establish such things that I know is through the Hanner inequality. This is a very neat inequality. So a norm space satisfies the p-Hanner inequality, where p is larger than 2, at least 2, if this inequality holds. If I look at the norm of x plus y raised to power p, then add it with the norm of the difference of x and y raised to power p, this is bounded above by the just sum of the norms to power p plus the difference of the norms to power p.
Is the p power missing on the x and y?
No, this is take the norm, take the difference. Yeah, there is an absolute value here. And when p is between 1 and 2, the direction is reversed. So you look at this, and it should be at least this thing. So it's a very simple inequality, and it turns out that it's actually hard to establish for many spaces. So there's this really nice paper of Keith Ball, Carlin, and Elliot Leap from '94, where they show that, so they kind of looked back at this classical inequality, and they showed that many of these inequalities that we are looking at, like smoothness, convexity, and type, cotype, they follow from this with right constants, with optimal constants. So in a sense, this is really something desirable to prove. If you can prove it, then you know all the right constants for all these other parameters. And so Hanner verified this for LP spaces in '56. That's why it's called Hanner inequality. And so amazingly, so the next natural class is Schatten norms one wants to look at. For Schatten norms, it is known for even integer Schatten norms. And exactly because they're combinatorial, because we can expand things. So that's due to Tomczak-Jagerman from '76. So she verified this for the basically C2K norm in our notation, the graph norms. And for other Schatten norms, it's conjectured to be true, but no one knows how to prove it. Okay, so one other thing is that, so in this paper of Ball, Carlin, and Leap, they kind of went around this Hanner inequality. So they kind of proved all the possible consequences that this might give us differently for Schatten norms. So we know the smoothness, convexity, type, cotype with right constants, but not using Hanner inequality. But if you can prove Hanner inequality, it gives a neat and short proof for this. Yes?
What was the Tomczak-Jagerman effort? Is sum of the eigenvalues squared?
No, it's just, it's exactly what I'm going to do for graphs now. So you just expand things. So suppose that H is a norming graph with m edges. If I want to establish m Hanner inequality, I have to prove this. Now, how do I prove this? So the left-hand side is really nice now, because I have this m power. That's just, I can write it as this is just the th of f plus g. This is th of f minus g. Let me write it in this product notation. So that's the left-hand side. Now, I'm going to expand things. So let even correspond to ones which have even number of g's. So when I expand them here, I'm going to get a positive +1 sign. And odd corresponds to the similar thing. So the same product of combinations of f and g where I have odd number of g's. Now, so what I have here is just even plus odd plus even minus odd. So depending which one is larger, I'm going to either get 2 even or 2 odd. And I can bound this using Cauchy-Schwarz type inequality. Just apply it to each term. So 2 even is going to be bounded above by this. 2 odd is going to be bounded above by this. So just apply Cauchy-Schwarz to each term and get. So it's really simple proof and gives the C2K proof of Tomczak-Jagerman and all the graphs. But yeah, it's a very combinatorial proof. So that's why you cannot generalize it to all the other cases. So in some sense, these norms behave similar to LM norms in many spaces, in many aspects. And now let's look at the norm with absolute value. This is more difficult to handle, actually. So for a while, I didn't know what's going on here. And actually, it turned out that this space, not only you can, so LM still is inside here. So it doesn't behave better than LM. But it turns out that you can also embed L1 spaces inside this. Not isometrically, but almost isometrically, with distortion arbitrarily close to 1. So it's a space, when you take this absolute value, it's a space which contains inside it both LM spaces and L1, almost L1 spaces. So there is no hope that it's going to satisfy M Hanner inequality. But still possible to go over this proof of Keith, Carlin, and Leap with a lot of difficulties, but it's possible to go and compute all the possible all the constants that one wants about smoothness, uniformity, and so on. or type and cotype. Okay, so in some sense it behaves, it's kind of like the best thing you can expect if you know your words than L1 and LM. And so a possible application, let me mention that, which might be familiar to combinatorists, is so there is this hypercontractivity inequalities which now have been used a lot in combinatorics. And Ben Arroyo, Oded-Regev, and De Wolf, they showed that you can deduce them from smoothness, from convexity, uniform convexity. So what does it mean? Let me just say the inequality. I think it might be useful in studying certain random graphs, not Erdos-Renyi, but more complicated random graphs, or some application in coding theory. Suppose I have a function from hypercube to mm, so from -1, 1 to k to mn, the space of matrices on n by n matrices. Mn is the space of n by n matrices. Then I can write a Fourier analytic expansion for f. So just write f as the sum of these f hat s's, which are matrices now, times this Fourier, like characters, Fourier characters that we think. Now, the hypercontractivity says that if you look at these H norms of these matrices, take power 2 and scale them down by this large constant, so by this constant, m minus 1 to minus s, the sum goes over all. So this is like, you apply Fourier coefficients, but you dampen it down. This, the large s's get penalized by this small constant. Then this is bounded above by this LM kind of norm. So you look at the expected value of f of x now is a matrix. So you can look at the H norm of it and take the power m. But now the right-hand side is something nice, because if you take the m power of this, it's like f of x gives us a matrix. So it's like picking a random matrix and then look at the edge density. So the expected edge density of a random matrix, if this is your random model, and take the power at 1n. So they use this for Schatten norms. And they had some applications in quantum computing and coding theory. They applied this for Schatten norms. Convexity follows from this result of Ball, Carlin, and Lieb with right constants. They took that result, proved this for it, and applied it to some problems about locally decodable codes and stuff, which I don't know exactly. But yeah, so it might be some similar applications using in this general form for general graphs. So I'll stop here.